All right, instantaneous power. So the idea behind instantaneous power is the same as it's been since your early days in circuits 1. Power equals current times voltage. And that's truly all it is. There's nothing more to it. There's nothing less. It's valid for any waveform at all. It doesn't matter if it's periodic or not. Average power only makes sense, though, if we're talking about periodic waveforms. And a brief thought process will show why that's true. It doesn't make sense to have an average of something that inherently has no average, that varies around. If you take a look at the standard definition for any kind of average, it is the integral over one period of P of t times dt. And that's true for any waveform at all. Any periodic, rather, waveform. And as a little aside for my advanced students, realize that the average power, which we're calling capital P as opposed to lowercase p, capital P, the average for any kind of function at all, is always going to be just the area underneath the curve from one time point to another time point of whatever your function is, divided by that distance. So in other words, if you've got a function and it's doing something like this, and you want to know what its average value is between here and here, you would find the area in this region, and you divide it by the length of this region, and that gives you the average value. So if we're talking about the average value of a periodic waveform, we'll take its integral over one period, over any period. So getting back on track, if this is the formula for the average power for any periodic waveform, then if it's a sinusoidal state system, we remember from our EE230, from our Circuits 2 class, that is equal to the maximum voltage times the maximum current times a half, and that's because it's sinusoidal. If it was just a strict DC value, it'd just be V times I, but since it's a sinusoid, it's 1/2 of the maximum value times the cosine of the difference in the angle between the voltage and the current waveform. So, I'm not sure we've got the schmutz down here. So, that's true for sinusoidal steady state. In other words, if our voltage looks something like a maximum voltage times a cosine, and we really don't care what frequency it is, but it's got this phase offset, and the current has got this maximum voltage that goes plus and minus to Im. Same frequency, different phase. Then all we really care about is the cosine of the difference of the angle. And because cosine's an even function, it really doesn't matter if you say theta v minus theta I or theta I minus theta v. It's the same thing. So this now gives us our clue about how we're going to measure the average power for a more complex waveform that we've deconstructed, that we've done a Fourier series analysis of, that's got lots of different frequencies. We can replace it with the DC part plus our very first frequency. And that will be, our first frequency is our V sub 1. And in fact, in general, it would be V sub n, I sub n. So I'm just copying up what's up here. I believe I used a lowercase phi for the voltage, and then same thing for the current. And since we've got a whole bunch of these different values of n, in fact, we've got an infinite number of different harmonics, we're going to sum those harmonics up from n equals 1 to, well, as many as we've got, all the way up to infinity. So this, you can read out the Fourier series components of each one. You can see its DC value, just plain old V times I, that comes from your very first semester of electrical engineering. And then these are just this for every single different frequency component. And so we'll say this is for a any periodic waveform with our voltage represented as a DC component plus that Fourier series of all these different harmonics from 1 to infinity of V sub n times cosine of, if it's a harmonic, if it's the nth harmonic, it'll be n times omega naught t. And of course, it'll have some sort of, in general, phase offset. Then we can say the same thing for our current. It's our DC current, and then to that we're going to be adding a whole bunch of these different harmonics. And our frequencies have to be the same, but our phases can surely be different. So let's back up and review quickly. What we found is an equation that lets us determine what the average power is. What's interesting is we found two different equations. One, which is this one, which shows how to figure out the average power of a waveform in one shot doing a single integral. But we found a much more powerful equation. We found this one. And this one says, again, what the average power is in a waveform. But this breaks it up into different frequencies. If you want to find out what the DC power is, what is the amount of power in a particular complex waveform caused by its average unchanging value, it's that. If you want to find how much power is caused by its first harmonic, its fundamental, it's this, setting n equals 1. Or for its 17th harmonic, this, setting n equals 17. You want to know why you might prefer the sound of a particular note, say middle A, played by a cello instead of played by a brass trumpet. It's because although the fundamental frequency is the same, the amount of energy of the higher harmonics is different, and that's what gives every sound its unique timbre, its unique sound quality, and it's very important in electrical engineering. Just imagine for a second if you were analyzing stock prices and you found that there was a particular spike when you were analyzing these stock prices over here for n equals, say, 6. That 6 harmonic had a very strong component to a repeating waveform. Then once you knew that, if you could figure out what the phase was of that 6 harmonic, you would know when to buy and sell in order to make a good profit. There is a rigorous way we can talk about how much power is in every single different harmonic. And one way is exactly what we've written up here. But let's say you just want to know what is the power in general of a signal. And it's just a signal that you've got on an oscilloscope. It's proportional to a voltage. When we talk about the powers of the different frequency inside a signal, what we're doing is we're pretending it's a voltage waveform. We're pretending we're sending it into a 1 ohm resistor. Because it's a 1 ohm resistor, V is the same thing as I. And now we can say that the power in a particular harmonic, in fact, of harmonic n. And when we say that, the understanding is that if it was a voltage waveform delivered to a 1 ohm resistor, but that's usually never said. Instead, we just simply say, how much power is in the nth harmonic? And the answer to that is, it is equal to A naught squared. In other words, this component right here, VDC, IDC, all of a sudden that becomes capital A times capital A because it's a 1 ohm resistor. If we're talking about its 0th harmonic, its DC term, or it's equal to 1/2 A sub n squared for n greater than or equal to 1. In summary, this is what I want you to take out of the lesson so far. You already know what the instantaneous power formula is, but that's an important one. We've talked about it from day one in electrical engineering. The thing from this lesson is this equation right here. This lets you say, given an arbitrary waveform, which we're going to pretend is the voltage being placed across a 1 ohm resistor, given that arbitrary waveform, how much power is in the 3rd harmonic or is in the 0th harmonic? And this gives you the equation to determine that. I've got another optional lecture, very short, that gives you an intuitive idea about what this is when applied to musical instruments. And then we're going to ask, and then there is a non-optional required lecture after this that describes the next segment, the last segment in this lecture series, which is an intuitive idea based upon this waveform, based upon this equation. And that is that if this is the power at DC, and if this is the power in any harmonic 1, 2, 3, 4, then if you add them all together up, shouldn't you end up with the total power? And the answer is yes, and that is what Parseval's theorem is.